Hello everyone. In this video, we are going to talk about hybrid force motion control example for a cleaning robot. Now, if you watched my robotics playlist, you know I have a video where I talked about hybrid force motion control and the theory of it, but I don't have an example, a physical example of it applied to a real case scenario, so this is that video. So to go very simple, we look at the 2DOF planar arm with both rotary joints and assume that the end effector is like a scrubbing pad or a cleaning pad. And the goal of this robot is to clean a wall or like a window or something. So the wall is at a specific location. We can show it by X of the wall. And the goal is that the y of the end effector starts from some bigger number and linearly goes to a smaller number. So basically what you need is in this direction of y, you need to have a motion control. So you want to control the y component of the end effector. And in the x direction, where the force is applied, you want to maintain a fixed amount of force so you can do a proper cleaning job. So in the x direction, as I said, the goal is to perform a force control. So here we want the fx to converge to fx desired. And in this direction, we want the y to converge to y desired, where y desired is linearly decreasing from a bigger number to a smaller number, from the max on the wall to the min on the wall, the range you want to clean. So clearly it's a hybrid force motion control. And the equation of motion for the robot, we go with the simplest scenario, so we can always apply voltages and damping and static friction and so on. But here we go with like the basic equation where you directly control the torques, and we only consider the accelerations, Coriolis, centripetal, angular accelerations, and gravity. And for the control, based on the video that I had on hybrid force motion control, we are going to do some feedback linearization. So we cancel the G and the CQ dot in the tau. So we have to have a sensor that measures for us the Q's and Q dots. So we can form these terms because G is a function of Q. And then here is going to be J transpose times F of the tip. So that portion here is the wrench at the tip. And in this case, since you only have X and Y motion, so that's basically Fx and Fy. Now the F at the tip, we bring it from two terms, PMFM plus PFFF, where FM and FF are the forces or the wrenches that you have for controlling the motion and controlling the force. And PM and PF are the projection matrices. PF to control the force along X direction and PM to control the motion along Y direction. And PF and PM are related. If you see PM is I minus PF. If you look at my hybrid force motion control, you see in that video, I used P and I minus P in that video as the two projection matrices. So that's the same thing here. Now, in this case, PF is N transpose, where N is the vector in the direction of force application. So this is N in this case. And of course, it is 1 and 0. Okay, or you can use a normal vector in this case. So N transpose is this matrix. And clearly, when this one is multiplied by any F, so if that F has Fx and Fy, right? The only thing that you will get out of that, if you look at it, when I multiply, it is going to be Fx and 0. So it will only keep the Fx for controlling the force in the X direction. In the Y direction, when you use PF, it will not apply any force. On the other hand, PM, which is I minus PF, and it's going to be this matrix, if you multiply this by any Fx and Fy, the result is going to be 0 and Fy. So the only component that this one will keep is the Fy, because in the Y, you need to control the motion. So you see, by multiplying these two matrices by different F's, you can only keep their X or Y component individually to control either force or the motion, not both at the same time. That's why we call them projection matrices. Okay, so let's move on. Now, if we show the position of the end effector X and Y as vector X here, and you know that the time derivative of that, which is xi, right, the twist, or x dot, this x dot is equal to j times q dot, right, based on the definition of Jacobian. Now, if you take another time derivative from this, then since j and q dot both have time derivatives, you will get j dot q dot plus jq double dot, so that j dot is time derivative of j. Good? Now, how do we proceed? So first thing is we plug in this control law into the equation of motion. So if we plug the torque into that, as I said, the C's and G's would cancel. So you will get mq double dot equal j transpose times this. Now here, you might say, why did you neglect this? Because right now, I just want to look at the motion control first. So if the motion control is my goal, then I can neglect the effect of that, because I only get this portion. So this is the equation of motion with the control law just for the y direction. Okay. And as I said, the pose double dot is going to be this. So now from here, I can solve for q double dot. If you solve for q double dot, you'll get what? You get m inverse, assuming that it exists, times j transpose times pm times fm. Good? Yep. So now that is going to go here. This solution is going to go and sit right here in the place of q double dot. Therefore, your x double dot is going to be what? J m inverse j transpose pm fm plus j dot q dot. Okay, so now hopefully you see where this formula comes from. So this is what? This is the end effector double derivative, or the acceleration in the workspace, basically, in terms of everything else so far, based on the control law that I picked. Good? So now what? Now that I have this formula that I derived, the goal is to pick Fm such that the y component of this, because this guy, as you know, is x double dot and y double dot. So first, I have to extract the y double dot out of this, which is the second component of it. In order to do that, all you need is to multiply it by a 0, 1. So, right, because if you multiply a 0, 1 by vector x double dot, since this is x double dot, y double dot, 0, 1, clearly the result is simply y double dot. So if I multiply both sides of this one and this one, and the left side by a 0, 1, then I will get y double dot. So now the goal is, again, what should I pick for this Fm such that this y double dot basically converges to yd double dot, right? Because when y goes to yd, then y double dot should converge to yd double dot. If I can pick such a thing, such Fm, then I can guarantee my motion control in the y direction. Good? So now, how do we pick? So before I move on, because this notation here in this box is quite a bit big, I'm going to pick some new notations to make it a little bit nicer. So what I will do is, this guy here, I call it lambda y, and this guy here, I call it vy. So I can write y double dot as lambda y fm plus vy. Now you might say, well, for lambda y term, they don't look exactly the same, right? The answer is yes, they do, but here I have to mention some specific thing. What is that? So first of all, you might say, well, look here. Here you had PM and FM. Here you don't. Instead, you only have a 0 and 1. Here, this FM is a vector. That FM does not have a bold font. So is that a scalar? The answer is yes. This FM on the right-hand side is a scalar. This one is a vector. What's the difference between them? The difference is this, that the FM vector is a 2 by 1 vector. The top component of it is 0. The bottom component of it is this scalar FM. Good? So first of all, that's the difference between them. Second of all, when I multiply PM by FM, remember PM is this. If I multiply this by FM, which is in this case is 0 and scalar FM, what would you get? Clearly, the result is basically 0 and FM. Yes? Good. Then what? Then here it is written as just FM. So I want to only extract the bottom portion of it. In order to extract the bottom portion of it, I need to multiply it by a 0, 1. Okay? And that will extract it for me. So in this case, my y double dot is going to be this formula that you can see up here. The y double dot, the acceleration in the y, is going to be lambda y fm plus vy, where fm and vy are both scalars in this case. Okay, they are both scalars. They only have a dimension 1 by 1, and this fm is also 1. So everything here in this underlying equation is 1 by 1. So now the question is, what do I pick this fm with these definitions for lambda y and vy? And lambda y is clearly the mass here, right? Or 1 over mass in this case. So operational mass, actually when I say operational mass, is kind of similar to 1 over mass, because force divided by mass is acceleration. And this J dot Q dot will basically include centripetal and Coriolis forces, but in the task space. So the question is now, again, what do I pick for Fm? So this y double dot converges to y double dot d, or y converges to yd. And the rule that is suggested here is this one. What kind of control is that? This one is a feed forward. And this here is a PD control. And again, this Vy, you can also call it a portion of the feed forward. Now, if you look at Vy, it's not really feed forward because it needs a feedback. So I would not correctly, if it's not correct to call it a feed forward, it is a feedback, but it is not an error term. There is no error term in it. So this one here is just a feedback term, but it's not an error term. So it's kind of a feed forward plus PD control. And why did we pick it the way it is? Where does this come from? First of all, the EY that you see here is the tracking error, which is the difference between this EY here that you see. This EY here is basically Y desired minus Y. Okay, that's your tracking error that you can see here. Good. Now, why is it picked like that? Well, that all comes from the aerodynamics equation. So if we look at the EY double dot, which is the difference between these two, it is going to be yd double dot minus. Now for y double dot, it is equal to what? Let's go and look at this. So this should actually, there is a typo here. So that should be negative of this. And this here, if you negate it, will be negative lambda y fm minus vy. Okay, yes? And then what? Then here for fm, or this scalar fm, I'm going to plug in this bottom here. So wherever I have fm, I am going to plug this for it. If I do that, there will be a lambda y multiplied by a lambda y inverse, which they can cancel each other, and then the remaining of it, the inside parentheses, will appear right here. So now what happens? As I said, these two will cancel, become an identity matrix. So now what happens? First of all, this y double dot and this y double dot would cancel. Then this negative of negative Vy becomes positive Vy, and that positive Vy and negative Vy would cancel as well. So all you will have on this side is a negative KDEY dot and a negative KPEY. On the left side, on the other hand, you have EY double dot. So now if you take these two negative terms to this side and arrange it, it is going to be the second order linear homogeneous ODE. If you pick your KD and KP properly, like positive definite, you can guarantee that the error will converge to 0, and that is exactly what you want. So here you can see that if I pick my control law like this is what I pick for my FM. This is PM here, which I don't need to pick. That is picked based on the direction of applied motion and applied force. And the torque that I pick is this one here, right? So I need to apply equations 1, 2, and 3. If I use 1, 2, and 3, right? And plug them back into equation star, which is my equation of motion, I will guarantee that the error will go to what? Will go to 0. And that is exactly what I want. So you now see why we picked FM the way we picked it. Because first of all, the reason I picked a lambda y inverse, because this FM has a lambda y in the back. So these two, they have to cancel. Then this y had a positive Vy, so I had to pick a negative Vy to cancel that one as well. So you see I'm doing again feedback linearization. And these two are from PD. I picked this one, so it will cancel this term in my error, as you saw, and I get my beautiful homogeneous linear ODE. Okay, I just cleaned up these and added some nicer notations and basically arrows, and instead of handwriting I typed, so, and I get rid of those small typos, so it looks better. So now if we look at the force control in the X direction, we use the same control law as last time, except this time remember that you're only doing force control, so we don't need this term. Tau is the same as last time. The C's and the G's would cancel, and you will get basically this. From here, you solve for Q double dot. You get this one, and then you can plug it into the end effector acceleration in the workspace. So you plug it here. And then if you're looking into the X component only, you need to multiply this by a 1 and 0, because this guy is X double dot and Y double dot. Okay, that's where this one comes from. So if you do that, then your acceleration in the X in the workspace is going to be lambda X FF plus Vx, where Vx is again these Coriolis and centripetal terms for X, and lambda X is kind of an inverse mass scalar term. Okay, now you might say, why are you looking at X? Remember, your goal in this case is f of X, to go to some f of X desired or something, correct? So why are you looking into X instead of f of X? The problem here is this f of X itself, because fx desired, let's say, is a constant value, okay? The problem is, how would you simulate f of X? If it was an actual robot, then guess what? For an actual robot, I have a device, any sensor, I talked about them. under my video called force control, ideal force control in my playlist. So there are all sorts of sensors from tactiles to torque sensors, wrist, and all sorts of 60 OF or less than 60 OF sensors, pressure sensors that I can feel the force between the pad and the wall. But for the sake of simulation, there is no way I can do that. Okay? So what I did is in my simulation, which I'm gonna show you in a second, I modeled the force of the wall by a simple spring or a compliant model. So I said if the x of the end effector is bigger than x of the wall, so it tries to move to the right. Now physically, you know, it cannot do that because the wall will not allow it, but the wall, I modeled it like a spring. So I said here, instead of this wall, I have a spring like this that is basically resisting my end effector x motion. So if the x that I have is trying to get bigger than x of the wall, even small, that k, the wall k times the difference between these two is the force that is being applied back to the path. And if it's less than that, because there is no contact, of course, there will be no force. So here, you see, I'm using a simple compliant model, and I'm modeling the force of the wall by a simple K. If I bring in a mass for the wall and a damper for the wall, and I model it like a complete mass spring damper system, then that is that impedance control that I talked in another one of my videos. So here, I just want to go very simple. So now what? Now, if I want to control the force in the x direction, all I need to control is x itself. Why? Because if I solve for x, if I say the fx desired, the one that I want, I either show it with fx star or fx desired. In this case, these are the same thing. That is going to be k times x desired minus x of the wall. And if I solve for x of the desired, I will get this. And remember, x of the wall is a fixed number, my desired force is a fixed number, and k is a fixed number. So if I can get my x desired to be a fixed value, right, and force my x to converge to x desired, or the error in the x to converge to 0, that is guaranteeing that my f of x will also converge to fx desired, or in this case, we call it fx star. That's the same thing. Okay? So here I convert the force control in the x direction to a motion control in the x direction, basically using a compliant model. And if I pick my FF, this guy here, to be basically a what? A lambda x inverse times the same thing as last time, the feed forward term plus a PD control plus this feedback term, then these two would cancel, these two will be multiplied and canceled. The x double dot term, which you have in ex double dot, because ex double dot is going to be xt double dot minus x double dot. Okay, and then that xt double dot and this xt double dot will also cancel. And again, you're going to get the second order linear ODE with constant coefficients. And again, if your KVF and KPF are again positive definite matrices, guess what? You can guarantee that your E of x goes to 0. Okay, so you see here, I'm converting it to another motion control in the x direction, and a simple PD plus feed forward and feedback should do the job. And actually here is my simulation. So the length for both members is 1.5 meters. K of the wall is 1,000. X of the wall is 1.5. And the force I want to have between the pad and the wall is 50 Newton. Now pay attention here that if you, because I give you a download link to download it and play with it, but if you want to change X of the wall here, this one, make sure it is within the workspace of the robot. Okay, so do not put something like 3.5 here because I cannot reach it. So it has to be within the workspace, and not just that, your Y desired here, which starts from 1 and then with a decrement of 0.05 per time, goes down to 0.2, you have to make sure the furthest point that the end effector should reach, which here is 1 in the y direction and 1.5 in the x direction, the distance, the radial distance from that point to the origin is no more than L1 plus L2. So the maximum radial distance I can reach is 3. So make sure the square root of wall squared plus what? This y0 squared is less than that. Let me actually add something here. So the square root of y0 squared plus x of the wall squared should be less than basically L1 plus L2. Otherwise, you will not have it in the workspace. And here a similar thing too, that x of the wall should be less than L1 plus L2 for sure. Okay, so you have to pay attention to these important things to be within the workspace. And then we have control gains here, of course, and I'm picking some control gains. Now for the y direction, I'm using an I as well to so I make it a PID instead of a PD to get rid of the zero offset. You can do a similar thing for the x direction if you want. The time goes from 0 to 10 seconds with increment of 0.01. This is the velocity of going down. If you want, you can make it bigger or smaller. I start everything for storing at 0. My initial condition is pi over 4 and pi over 4. My velocities and accelerations are both 0 in the beginning. And then I run my for loop where it calculates basically the angles, correct, and then the velocities. Then, of course, it performs the forward kinematics, Jacobian, M, C, G, correct, and then everything else that needed. And, of course, calculate lambdas, V's, and then calculating the acceleration terms, the Fy, the Fx, which are the same as Ff and Fm in this case, plugging them, and then calculating the torque, plugging into the system, getting the accelerations, and then updating the accelerations twice. So this is 2 times time integration to get Q dot and Q. Finally, you can do the plots here. And look here, if I do that, you are going to see, look, you are going to see that y desired starts from 1 and goes down to about 0.5. Now, why 0.5? Because the speed is like that, right? So if we go back, look, this y desired should not really be 0.2, so that could be a little bit misleading, okay? But that is like the final value. This is the actual y desired that you will use. And you see it is using a linear formula. So that yd here is just like the bare minimum. You don't want it to go below 0.2. It's like, for instance, here on this wall, I have an obstacle or something, and I don't want to go below that. Okay, otherwise it hits something. So it's not really a critical number. What is important is initial value and the speed. So if you want it to go down from 1 to 0.2, that's 0.8, and you want to do it in 10 seconds, so you have to do 0.8. Then it goes from 0 to 0.2, and then let's see here, if you run it again, there we go, look. So now it is going from 1 to 0.2. That is your desired y. Your initial y starts from 2.5 because your angles are 45 and 45, but very fast it can catch up and converge, so the error goes to 0. This is your desired force, 50 Newton. Your initial force is very big, like 400 something, but very fast the system adapts to bring the contact force down to 50 Newton. So you see now, literally, you have controlled the force between the pad and the wall, and you could allow the y to follow your desired y so it can perform its cleaning job perfectly. So this was an example of hybrid force motion control with the compliant model for the force on the wall. Hopefully this video helped you. I give you a download link for the code, and I'll see you in the next lecture. Thank you.